In this video, we start deriving the energies of the stationary states of a rigid rotor. A rigid rotor is a simple model of a particle of mass mu rotating at a fixed distance r around a center, essentially moving on a sphere. This is an excellent model for the rotation of a diatomic molecule, in which case the mass of the particle, mu, is the reduced mass of the diatomic molecule. The moment of inertia for the particle is I equals mu r squared, and its kinetic energy equals to T equals L squared over 2I, where L squared is the square of the angular momentum, L equals I omega, where omega is the angular frequency. Since this situation has spherical symmetry, it's most convenient to treat this problem in spherical coordinates, r, theta, and phi. Now, r is constant, so the particle has only 2 degrees of freedom, theta and phi. It can now move freely on the surface of the sphere with a constant radius r. To determine the stationary states for this quantum particle, we need to set up and solve the Schrodinger equation. It is h hat operating on y of theta and phi equals E times y of theta and phi. The wave function for the rigid rotor is conventionally indicated by y and not by psi. Since the particle can move around on the surface of the sphere without constraints, there is no potential energy term. We therefore need only the kinetic energy term in a Hamiltonian. H hat equals T hat, which is equal to negative h bar squared over 2 mu nabla squared. In spherical coordinates, this is a somewhat lengthy expression. T hat equals to negative h bar squared over 2 mu times 1 over r squared, and now in square brackets, 1 over sine theta partial dd theta operating on sine theta partial dd theta plus 1 over sine squared theta partial d squared d phi squared, which is valid only under the condition of a constant r, which is our assumption in this model. The first term of the operator in the brackets looks intimidating. However, if you attach a generic function on the right at the back and then work from right to left step by step, it's easy to evaluate. The denominator here in the prefactor contains mu times r squared, which is the momentum of inertia, I. Comparing this expression now to the classical expression for the kinetic energy, L squared over 2I, we see that we can write this as L operator squared over 2I, where the L operator squared equals to negative h bar squared times the entire expression in the square brackets above. Okay, next let's insert the expression into the Schrodinger equation. We'll perform a few transformations on the fly. First we're going to multiply by negative 2I over h bar squared to remove the prefactor. Then we're going to multiply by sine squared over theta to remove the denominator, sine squared theta in the operator itself, and then we're going to move the right hand side to the left. This gives sine theta partial dd theta operating on sine theta partial uppercase y d theta plus partial d squared of y d phi squared plus beta times sine squared theta times y equals 0. Beta is an abbreviation for 2ei over h bar squared. Now this is a partial differential equation with two variables, theta and phi. To solve it, we can try the standard approach, separation of variables. we make the ansatz uppercase y of theta and phi equals uppercase theta of theta plus uppercase phi of phi, where theta and phi uppercase are the functions to be determined. Inserting this into the previous equation and dividing left and right by uppercase theta, uppercase phi, we get sine theta divided by uppercase theta d d theta of the sine of theta times d uppercase theta d theta plus beta times sine squared theta plus 1 over uppercase phi d squared uppercase phi d phi squared equals 0. Now, the first two terms depend only on theta, and the last term depends only on phi. Varying phi could potentially change the last term, but not the first two. The sum of all three terms, though, has to remain 0. So if the last term were changing with varying phi, then we would break the equality. Therefore, the last term must be a constant, independent of the value of phi. We'll call this constant minus m squared for future convenience. In analogy, the sum of the first two terms must be the negative of the same constant to give a total of 0. This constant will be plus m squared. We therefore have now two equations. The first equation is the equation for phi. 1 over uppercase of phi d squared uppercase phi d phi squared equals negative m squared. The second equation is the equation for theta. Sine theta divided by uppercase theta times d d theta operating on sine theta d uppercase theta d theta plus beta times sine squared theta equals plus m squared. We are going to solve these two equations separately. In summary, we have set up the Schrodinger equation for the rigid rotor. The rigid rotor is a particle that can move freely on the surface of a sphere and has 2 degrees of freedom, theta and phi. The wave functions are denoted by uppercase y. Using a separation of variables, we've managed to split the original Schrodinger equations into two simpler ones, one for phi and one for theta.